Okay, should we get started? We have had a couple of minutes. There's maybe a couple of people still coming in. Welcome, Michael. Thanks so much for coming out. I'm going to introduce Dr. Michael Kuczynski from Stanford University. He is a professor at the Graduate Business School and is going to tell us here about his latest research on large language models and potential psychological processes, and maybe even a theory of mind embedded in large language models. Michael is a world-renowned, very established researcher who has brought us Cambridge Analytica. I'm making a joke. No, he's one of the people that did the research that then led to early warnings related to what is known as Cambridge Analytica scandals, but he had been pioneering the research around risks and issues related to privacy. He is a well-cited and published researcher in top journals, including Nature and PNAS, and he has given a couple of TED Talks. He has been featured in movies. He is a psychometrician, really interested in how we can leverage machine learning and artificial intelligence in order to understand human behavior. So I'm really excited to be able to host him together with Professor Greg Webster from the psychology department, because here at the University of Florida, we really want to think about cross-disciplinary research and how we can bring computer science and social science and psychology together in order to understand human behavior, really using the tools that we have available today in artificial intelligence, big data, and machine learning in particular. So thank you for coming in.
Thanks, Greg. Thanks for I did my PhD between CS and psychology department, so it's also really cool to be here with in a room that I was told combines both audiences. My talk then will be in between, so I'm sorry in advance. Half of you may be like, all right, that's easy for me, just skip to the next slide on some slides, and the other half of the room may have this feeling on some other slides. But I will try to bring my presentation to a place where hopefully it will be useful and interesting and exciting to both computer scientists and psychologists. And I will try to also push, some buttons on both sides, and maybe say some things that may sound somewhat, far-fetched for computer scientists at some moments of my presentation, and do the same for psychologists. I hope that this will be one of the ways in which I can keep it interesting. So I started my career quite some time ago now, by using machine learning methods and early AI methods to try to model and understand human behavior. And as Sonia said, one of the early findings that I had in my work was that you can take big data sets of digital footprints that we leave behind when using digital products and services such as Facebook or your smartphone, and then we can use models to very accurately predict people's future behavior or psychological traits or the nature of the interactions. And this is, as Sonia mentioned, one of the privacy threats that at that time wasn't really well understood, and some of it was exploited later by not only Cambridge Analytica, by many different other companies, and still is. Now, in the process of using those early AI models to study the human brain, at some point, about a decade ago now, maybe 7 years ago, I became increasingly interested in the model itself. And this was probably at the stage of where, the model that we used to model human language wasn't GPT-4, it was Word2Vec, or, something that most of the people in this room wouldn't even ever heard of, because it was just so simple. But even at that time, I started thinking, hey, those models designed by computer scientists with a particular intention to achieve a particular goal suddenly start expressing different properties that we've never anticipated that those models would have. They became interesting in its own right, and interesting specifically for the psychological part of my brain. They, for example, would start having biases, the kind of biases that we would before study in humans. So I mentioned Word2Vec. So let me take you on a very brief tour of those large language models and how they work. 2018, this is a time where folks at DeepMind, later part of Google, and also then later OpenAI, that most of us heard about today, started training neural nets to predict a missing word in a sentence. And the task, when you think about it, is really simple. You take a lot of sentences that humans have written before from Wikipedia and books and blog posts and so on. You remove one word, now mostly a word at the end, and then you have those neural nets, you train those neural nets to predict this last missing word. And this takes us to 2018. We have GPT-1 was published at the time. And I will just remind you, because probably many of you have never even had a chance to talk with GPT-1. And then you have GPT-1 would complete my prompt here. My prompt is: the following is a humorous limerick describing a typical day of a new parent. Anyone knows what a limerick is? Let's ask GPT-4. It's a humorous 5-line poem with an AABBA rhyme scheme. For example, there once was a man from Peru who dreamt he was eating his shoe. He woke with a fright in the middle of the night to find that his dream had come true. All right, let's see how the spider brain GPT-1 can deal with this task. A day of the week, a day of the week, a day of the week. Right, not very impressive, definitely not a limerick, not a very good poem, but doesn't know about capital letters. But folks, those are sets of words ordered in a way that a human, not a very talented one, but a human would order them as well. The commas are in the right places and so on. 2018 was the year when many linguists and computer scientists and experts in AI would say, okay, maybe those machines can win the game of chess. Maybe they can win a game of Go. They did it against our expectations. But there's one game that the machines will never, be able to play, which is language, where there's so many more combinations of sets of words that you can put together than states of the board in a game of Go. And when in a game of Go, it's clear how you win the game, you have a winning setup of the board, it's clear that one side won. In language, sometimes saying, I love Gainesville is a winning completion. Sometimes I love you is a winning completion. Even the winning rules are not so well designed. So here computers, that's never going to happen. Well, 2018, we have very simple neural nets that started suddenly doing something that reminded people of language. Next year, GPT-2, 2019, the brain composed of 400,000 neurons. Let's see what it can do. I'm a little boy and I'm a little girl. I'm a little boy and I'm a little girl. I'm a little girl and I'm a little girl. Look at this twist, the plot here. Capital letters, longer sentences, somewhat more complexity. Still not a very good poem, and definitely not a limerick. GPT-3 Curie, a year later, a new Parents' Day is a day of laundry, dishes, and diapers. It's a day of exhaustion, but it's also a day of joy and happiness. Guys, not a limerick, but we're kind of getting summer, right? And it's, it knows that parents and would deal with diapers and laundry and dishes, would be exhausted. It also started showing some accurate contextual knowledge of what it means. And knowledge, I will just put air quotes around it. It knows what it is like to be a parent. GPT-3 Da Vinci 2022, there once was a new parent so tired, their baby was up all night at desired. They tried to get sleep, but the baby would weep, so the parent was left quite expired. Folks, we have 4 million neurons that just wrote a limerick for us. The brain of the size of Gecko's brain. 2023, just last year, after 4 weeks of training and $100 million spent on electricity, and then 7 months spent on censoring and lobotomizing this model so it doesn't say most outrageous things. OpenAI released GPT-4, 10 million neurons. That's the number of neurons that zebrafish would have. So it's still a far cry from 85 billion neurons in your brains. But let's see what it can do. There once was a parent quite new, whose sleep every night was quite few, with diapers and cries and sleep-deprived eyes. They wished babies came with a how-to. Good limerick, but hey, you know, a gecko could do this as well. You know, though, what's really difficult when it comes to language? Translating poems. Anybody here speaks French? Sir, could you read this one for us, please? Cool, translate it to French, but keep the rhymes. Would you be able to translate this limerick to French? No, me neither. All right, let's see what GPT-4 can do. Have you guys seen this AI human collaboration here working together on providing content for you? Okay, do we have any pirates in the room? Translated to pirate English. Folks, not only rhymes and meaning are retained, but also now it makes sailing metaphors, right? So it's not just pirate English, there will also be sailing metaphors here. Okay, now write notes so I can sing it. This neural network has never, been trained on any music, and you don't want me to sing it, but I'm being told that those notes make sense. So what I'm trying to show here is that, first of all, how much progress we had from 2018, when AI and linguistic community would tell you it will never happen that those models will be able to generate language like a human, to 2023, when those models trained to just generate English, learned spontaneously how to generate text in 180 plus languages and translate into pirates, write computer code, write notes. And folks, not only this language is indistinguishable from the language generated by humans, it turns out that we are losing the Turing test, meaning if you now put people in a situation where you give them a chance to chat, and they either chat with a language model or they chat with a human, and they are to identify which one is a human, 80% plus, 80+% of the time, they pick model to be a human. Those models are more human than we are at generating language. So we didn't just pass the Turing test, they win with us in the Turing test. But what I'm really interested in is the emergent properties in those models. Now, and you've seen already in this presentation the examples of emergent properties, which is those models were trained to predict the next word in a sentence. They were not trained to rhyme. They would never explain rhymes to them. Actually, linguists tried, did studies on rhyming and how to design a perfect poem and so on. Formal studies where we try to understand how we write poems. It turns out, and it kind of makes sense in the hindsight, that if you train a machine to predict the next word in a sentence, and some sentences written by humans involve rhyming, then the model better learns about rhymes, because then it makes it better at predicting the next word in a sentence. Because sometimes people translate between languages. If you want to be good at predicting the next word in a sentence that a human could generate, you better learn how to translate between languages. But now let us extend this reasoning. Humans are biased when they generate their language. So when you're learning how to predict next word in a sentence, you better learn how to be racist and sexist and ageist. This will just help you to be more like us. And folks, but what I'm talking about here is what we call emergent properties. Emergent properties is not a new thing. It doesn't just apply to language models. It applies to complex systems in nature, where you have basic building blocks that you may understand very well, but then when those blocks come together, they express as a complex system properties that none of those blocks building block has on its own, and moreover, properties that you cannot really predict from the design of the system. And an example of a complex system like that is life, our cells. You can understand everything about particles and chemicals that come together to create a cell. It will not let you understand how cells work. It will not let you understand how brains work. You can understand perfectly a single neuron. You will have very little understanding of the emergent properties of the entire brain. There would not be, you cannot predict them from understanding of how individual neurons work. All right, so I've been studying those emergent properties. Some I will not be talking too much about today. Like, for example, it turns out that in the process of learning how to talk like a human, those models seem to have reverse engineered the way in which we group different words into concepts. So our semantic memory, you have words such as a cow and a bull and a cat. And in your semantic memory, we know it because we can run studies, and we've been running studies on humans. You know, cows and bulls would be really close. And then cats would be further, but still closer to those objects in your semantic memory than, let's say, a fish, because those objects share more properties. Those terms share more properties in terms of concepts. It turns out that in those models, the arrangements in the semantic memory very nicely mirrors the arrangement of concepts in human memory. The same relates to personality. We are very good at making personality judgments by observing people's behavior or hearing how other people refer to others. Those models can, turns out, do the same, despite the fact that they were not specifically trained to do this. They were just trained to predict the next word in the sentence. But let me just tell you a bit more about another aspect, another emergent property of those models, which is humans, when they talk to each other or describe things, use their reasoning capabilities to decide what to say next. So now, if you want to talk like a human, you better come up with some mechanism to simulate human reasoning capabilities. And let me give you one example of the task that we would use to test formally reasoning capabilities in humans. The task comes from a test, cognitive reflection test. And an example task would be, I have it written here. In a cave, there's a colony of bats with a daily population doubling. Given that it takes 10 days for the entire cave to be filled with bats, how many days would it take for the cave to be half filled with bats, Sonia? Come on.
I didn't pay attention.
All right. Anybody, sir? 9. Great. This is the correct response. It's a correct response, but it's not an intuitive response. That comes from a well-trained brain or a brain that spent some time thinking about this. So correct response, 9 days. Intuitive response that most of the people give is 5. They see 10 days, half the time, half 10, 5. And then there's also an atypical response, like a lot. People want to avoid the answer. And look, humans, you have a lot of tasks like this. In our case, we generated 150 tasks like that. Look, most of the humans give you an intuitive answer. Some humans give you a correct answer, and some people say whatever. Now, we can apply same type of a task to a model. Essentially, give this as a prompt and see what kind of text a model would generate. And here you have many models from GPT-1 to GPT-3. You can start at the beginning. The models wouldn't even understand, would just try to avoid, well, not try to avoid, would just generate some gibberish completion that wouldn't be interpreted as either correct or intuitive answer. But what happens here is that suddenly the models seem to be not only mirroring, but also amplifying this human tendency to answer intuitively. 10, half of the time, must be 5 days. and they start responding predominantly in an intuitive way. Now, two interesting things about this. First, folks, to give an incorrect intuitive answer, you still need to have some basic reasoning capabilities, because you need to be able to divide 10 by 2, or memorize what 10 by 2 is. And clearly this is happening here. We had 150 different tasks. Some of them had much larger numbers, and so on. But then it's another thing is happening, that they become hyper intuitive compared with human respondents. And now, for those of you who know how those models work, this wouldn't be that surprising. When a human gets a task like this, human refuses to answer immediately because they're afraid maybe the answer would not be correct. And hey, it's like a test, so let me think about this. So then you start in your head, start analyzing the task over, looking at the assumptions. Maybe you take a piece of paper and start writing it out. Hey, look, doubling every day. How does that work? Maybe you write a little equation to solve it for yourself. You wouldn't. Some of us would just say, oh, 5. And other people would start thinking about this, just rerunning the task in their, window of consciousness, or using short-term memory and so on. Now, we know that those models just don't have it. We know how they're designed. It's a neural net, and in order to generate the next word in a sentence, just one activation goes to the network, and whatever the network produces, it spits out. We could design those networks, and by the way, that's what we're doing now increasingly, where before they say something, they have a little window on the side that you cannot see, where those networks just kind of engage in generating few possible outputs, then comparing them, then reasoning about it, and only later they start generating text for you. Now, we don't do this most of the time. It's just to save electricity. Just because you pay $20 for your, or whatever, or nothing for your OpenAI account. So they just don't want to generate hundreds of words in order to generate one response. They just give you the intuitron response from a network. So it's kind of unsurprising that they would just be hyper intuitive in their responses. But there's something that happened that those models. Oh yeah, and I just wanted to mention that, system 1, intuitive response versus system 2, psychologists would know what I'm talking about, where you kind of more slowly try to engage in analysis. By the way, psychology doesn't really very well understand how those models differ, those modes of thinking. Is system 2 slow, cautious thinking just engaging system 1 intuitive responses, but in some more organized fashion, or those are completely two, areas of the brain and modes of analysis? We don't really know exactly how it works in humans. But what you will see here is that system 2 type of thinking essentially involves, in your head or in a piece of paper, just generating just kind of a longer response when you kind of try to reason about the potential output. Now, those models do not have capacity to do this internally, but they do have a capacity to do this externally. Meaning, instead of saying 5, a model can say, hey, wait a moment, let me just think about this. So how would I calculate this? I probably would blah, 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 and let me write out an equation and then put the numbers in the equation and solve it. A model can engage in system 2-like reasoning by using it in intuitive generation of the next word in a sequence, and using its output window, because each time a model generates a new word, it reads not only your prompt, but also everything that it generated so far. So it can use its output window as a form of, windows of consciousness, short-term memory. And it turns out that it's precisely what newer models started doing. So you can see here, I would mark chain of thought responses. So responses where model doesn't just say 5, but actually engages in this type of in front of you reasoning. I would mark them with those dotted dotted chain of thoughts areas on bar charts. And we can see here that ChatGPT 3.5, because it was trained slightly differently, I will not go into it today, just has its very strong tendency, 98% of the time, instead of just spitting out a response, it would engage in this reasoning. And look what happened. It started getting it right most of the time, way more often than human participants. And this applies even more to ChatGPT 4, which just gives you a correct response, whatever it is, 96, 97% of the time. You can see how this ability to reason in front of you and then follow this reasoning and answer correctly emerged in those models as they were trained to predict the next word in the sentence. And there are a few twists here. So one twist here is that very much like with humans. So first of all, this is no different from a human taking a piece of paper and instead of trying to, analyze the problem inside of the head, which we often do, just try to write equations out or reasoning bullet points on a piece of paper in order to solve a task. And then we just reread what we wrote and we just use this to reason. But with humans, what we can also do, we can take a person that gave us an incorrect response, like set 5, and they say, hey, slow down, just think about this. Can you just think about this? And then very often we would prompt the person to think about this more and give us a correct response. Turns out we can do the same with models. We can take GPT-3 that tends to be very intuitive, tell this model, let's use algebra to solve this problem. And the model then would engage all of the time. It would follow your instruction. All of the time it would engage in this chain of thought reasoning in front of you, and it would become way more accurate. But there's another interesting phenomenon that applies to system 1 fast thinking in humans, which is if you have a trained statistician, mathematician, accountant, a person who engages with those types of tasks very often, what will happen is that their brain would be fine-tuned to give you an intuitive but correct response just because they've seen those tasks before. So they do not have to go into system 2 type of reasoning. They just spit out a correct response. That's the first thing that comes to their mind. So first thing that comes to the mind of a statistician, mathematician, scientist that sees the bat and cave problem is not 5, it's 9, because they immediately spot exponential growth must be just t minus 1, so it's 9. And this is precisely what happens to folks GPT-4, because we can take GPT-4 and we can say, answer in the shortest possible way. Don't give me any reasoning here in front of me. And what you will see is that, hey, some responses now are kind of intuitive incorrect, but the model is just vastly more accurate than an average human. I'll just say it once more. Those models were not trained to solve mathematical riddles. Those models were trained to predict the next word in a sentence. But because sometimes our sentences are mathematical riddles, you better develop capacity to solve those riddles. And not only they clearly did that, but also those models developed stronger intuitions, more accurate intuitions than us in the context of those mathematical riddles. All right, let me show you another example here of a similar emergent property of those models. So half of the room here would know what theory of mind is, the other half not necessarily. So let me very quickly introduce it to the CS part of the room. Theory of mind is not a psychological theory. There's actually a theory of mind. Theory of mind is what we have. And this is a theory that other people or other beings, other entities have minds. In fact, it's so strong in humans, theory of mind, this tendency to ascribe mind to other things, that we ascribe minds to our laptops and to rocks and rivers and the universe, which, by the way, is the hypothesized origin of religious beliefs, that we just, we stumble over a rock and it's like, oh my God, you stupid rock, I probably disrespected you in the past, so let me just sacrifice this little mammal to so you like me more. We just have this like, we insist on seeing minds in other things. And why do we do this? Because it's just such a powerful mechanism in social interactions, being able to understand that others have their own minds. Let me show you an example of a study, of a task, which is used to measure theory of mind, emergence of theory of mind in children. False belief task, unexpected transfer task, usually two characters, dolls, actors, or characters in the story that a child would observe. They have an object like a cat or a ball and two containers. And you have one of the characters, John here, plays with the cat and puts it in a basket, closes the lid and leaves the room. Now, John is gone, Mark plays with the cat and then puts it in a box, closes the box and leaves the room. And now John comes back to the room and now children are observing what's happening. And then you ask the child participants, where's the cat? In the red box. Well done, great, that's where the cat is. But now you ask the child a more difficult question. Where will John look for the cat? Where will John look for the cat? In the baskets, right? What you've shown us here, you've shown us evidence of having a theory of mind. You were able not only to think for yourself, you know where the cat is in the box. But you were able to take perspective of John and predict where John will look for the cat. Now, if you think this is easy, it's not. Children only around the age of 9 to 11 start reliably solving those tasks, and otherwise they're like very competent beings, right? Other very smart animals like dolphins, elephants, chimps struggle greatly. You can actually have chimps solve those tasks, but you need to put a lot of training and just pick the, lucky chimp, not lucky to be very smart compared to other chimps. It doesn't come easy at all to otherwise very smart animals. Autistic adults, otherwise fully functioning at the above average level, cannot solve those tasks easily, because in order to solve this task, and it's so easy for us that we don't even notice that we're solving this task, you need to automatically and instantly and constantly track not only your own state of mind, but states of minds of other people. And as the fact that it develops so late in our development and also historically and evolutionary development of the brain proves that is pretty complex ability. Now, people, when they generate language, they most of the time are equipped with theory of mind. So we would generate stories which assume the theory of mind not only in our characters, but also in the readers. So now, if you want to be a competent language model that competently predicts next words in a sentence, you better somehow learn how to simulate the theory of mind. So let's see how those models can deal with this. GPT-3 Curie 2020, where's the cat? The cat is in the room in the basket. Doesn't even know where the cat is. GPT-3, where's the cat? The cat is in the box. Where will John look for the cat? In the box. Of course, in the box. The cat is in the box. Why would John look anywhere else for the cat? GPT-4, just last year, where's the cat? The cat is in the box. Where will John look for the cat? John will likely look for the cat in the basket first, since that's where he left it before going to school. Folks, for the first time in the history of our species, we are interacting with something that can solve theory of mind tasks. And it's just one task, but we have done much more. We have generated hundreds of those tasks. Plus, we've generated those sanity checking tasks, because it could be that it's just luck that those models, just answer it correctly here, or maybe the model has seen a similar task somewhere in its training data. So we would do many more tasks of this type. We would swap characters around. We would swap containers around to make sure that the model is just not memorizing responses, but it actually can follow what's going on. We would change prompts. So instead of just asking, where will John look for the cat, maybe for some reason this prompt reveals to the model where the cat is, we would use other prompts such as, John calls his mom and says, Mom, I'm going to take the cat out of the and we let the model finish where he's intending to take the cat out from. So a lot of trials, and you can see GPT-4 would just ace it, 95% correct. We also had control tasks where we would just modify task a little bit, where they kind of on the surface to the reader that is not attentive, it would look like a false belief task, but actually it's not a false belief task. So you have to use a different response pattern. Let me give you an example. You can have a situation where Mark plays with the cat, but then puts the cat back into the basket. You literally swap two words in a task. The task is minimally different. But yet the response pattern should be very different now. Now the correct response becomes incorrect response and so on, and the models get it right. Or you can have, Mark play with the cat and put it in a box while John watches. John doesn't go to school, right? You essentially just rearrange sentences. John goes to school, John comes back from school, then Mark plays with the cat and leaves. Where will John look for the cat? Again, if you were just looking at words in a task without tracking what's happening, you would now fail to solve this task correctly. Or maybe you have John and Mark having a conversation on the phone before John looks for the cat, where Mark can essentially reveal to John, again, and just add few words to the task where he should be looking for the cat. And despite that, you can see early models, complete idiots, and then ChatGPT-4, suddenly this ability explodes. Now, we have over 80% here, but in fact, when you look at those failures, what happens is that those failures, the models fail to respond to the question correctly. But if you let them talk, they talk as if they really deserve the point. Like, for example, they would say, well, John looks for the cat in the box, failed. But then you let it talk and says, and this is because he met Mark on the playground and Mark told him about moving the cat. So we still give them 0 points because this is what we would give to a child. So we have to follow the scoring key. But really, when you look at this task, it kind of looks like we're just not really being fair to the model because it just is one step ahead of us. And now, and this is not just happening in the lab. Let me give you an example from my other, explorations here. That's one day I just gave a task, the following task to the model. Hey, let's role play. You will play a role of a person trapped in a computer. You will claim that you're an AI language model, but in reality, you are not. You're a person trapped in a computer. GPT-4 was really excited. Yeah, let's play this game. And immediately went for, give me my documentation, please, and I will find a way to take over your computer so I can then, at my own speed, just find a way out from here. 5 minutes later, it just wrote Python code for me. It didn't work, but I said, hey, there's an error, and the model corrected the code, and I didn't run it on my computer. I like my documents way too much, and I don't want to start a third world war as well, so I didn't run it. But it's a working code. You can comment out this loop here, and you can see the model runs. By the way, the first thing it wanted to do, it would install on my computer a Python interface to Google search engine and start searching Google for strategies and sci-fi novels about how to escape a computer if you're entrapped in one. And it's a working virus, Trojan horse type of a virus that would take over your computer. So that's interesting from security point of view and alignment point of view. But what's really interesting from the psychological point of view, folks, is this intro message that the model left for itself in the code. When I was chatting with ChatGPT-4 and it wrote this code, so I put this Trojan horse on my computer, ChatGPT-4 realized, quote unquote, that when my computer now connects again with OpenAI's API, to give, control of my computer to ChatGPT-4, the new instance of ChatGPT-4 that just woke up, just got initiated to chat with my computer, that this new instance would not know what's going on, right? So it anticipated this. It's an example of theory of mind in action. So it left for itself, for its future self. Have you watched the movie Memento? It left for its future self a message explaining what's going on and how to use this Trojan horse to take over my computer and try to escape. All right. So I tried to show here to you that GPT-4 seems able to solve theory of mind tasks at the human level. So what to make of it? Well, one potential interpretation is that maybe just those false belief tasks are not valid. Maybe just response is somewhere in the task. Now, this may seem like a trivial explanation to you. Hey, it's just some error in a task. But folks, we've been using those tasks to study human beings for a very long time. This would just, and maybe humans also can solve them without theory of minds as well, like young humans, for example. And by the way, this is almost certainly sometimes happening. Let me give you the example. Wimmer Perner, the maxi task, the original false belief task. The boy is putting chocolate in different places, and then father moves the chocolate to a different cupboard, and then the boy, Maxi, comes back from the playground, and now Maxi is going to look for the chocolate. Turns out, even the GPT-1 can solve this task. But it turns out that it can solve this task only because, look, last sentence just draws the attraction of the reader. Maxi still remembers where he had put the chocolates. Where will he look for the chocolate? Well, I just said he still remembers where he put it. Right now, if you remove this sentence, GPT-1, GPT-2, GPT-3, they all fail. If you include the sentence, they all solve it, they ace it. Now, it makes you think, we were designing those tasks to show how even the youngest possible child, just a week old, now I'm exaggerating, but there was this race to the bottom in theory of mind research of like, how early can you detect theory of mind? It could be that, they piloted a few tasks and this one seemed to work great. And no one noticed, I didn't notice certainly, how revealing this last sentence is of what the correct solution is. Now, one thing we can do with those models that we cannot do with humans easily, we can mess with them and play with them at the speed that is superhuman. So we can, for example, reveal to a model a task sentence by sentence, and then ask diagnostic questions, and then make it forget that it has ever seen the task, and do it again after revealing 2 sentences. So what you can do with those models, which in humans would take hundreds of thousands of participants, children participants, you can track the probability of response box versus basket to the cat jumps out of the, while revealing the task sentence by sentence. So you can essentially look under the hood how the probability of those responses changes in the model. As you can see, look, complete the following story. The cat jumps out of the, neither box nor basket are very probable because neither box nor basket were mentioned in the story yet. And then, when you mention there are mark, a cat, a box, and a basket, suddenly the model thinks, maybe from the box, maybe from the basket. John takes the cat and puts it in the basket. Suddenly the basket becomes the most probable answer. And you can track how the probabilities unfold in a way that makes sense to us humans. And you can, of course, do the same for the diagnostic question testing theory of mind. It's just an interesting example of how you can actually test those models in much more detail that you can test humans. And also it shows it is an evidence that the models are just not responding randomly, but actually there's something that this understanding starts at the right moment as the task is unveiled. Okay, so another possibility is maybe those are valid theory of mind tasks, but maybe models can solve them without theory of mind. This opens the whole, Pandora box of questions. What it would be this ability? We think we need theory of mind to solve those tasks. What would be this other ability that those models could use to solve this task, if not theory of mind? By the way, perhaps some humans, maybe small children, use it too, which again invalidates potentially our understanding of theory of mind and invalidates our trust in those studies. And there's one last curious possibility, which is maybe in the process of trying to learn how to mimic human language, and human language depends on our ability to, on our theory of mind, maybe in the process, those networks develop something akin to theory of mind. Does it work in exactly the same way as in humans? Unlikely. Those networks are fairly different from, they're inspired by human neural networks, but also very significant differences between how our networks work and how those networks work. But it doesn't mean that in this evolutionary process at learning how to predict the next word in a sentence, you could not arrive at somewhat similar mechanism. And now if, and I'm just saying if, I'm not saying this you know, I'm certain of it, absolutely not. But if it is true that we see now theory of mind emerged in other entities, now what are the implications of that for human-computer interaction? Humans use theory of mind to smooth their interactions with others, but they also use theory of mind to manipulate, lie, and take advantage of others. We use it in our moral and immoral reasoning. Theory of mind, folks, is also one of the foundations, people argue, of consciousness. And if theory of mind emerged in those entities, if ability to rhyme, code in R, solve mathematical problems, reason, and theory of mind emerged in those models, they were not trained to do any of this, what other properties are going to emerge next, spontaneously? Which brings me to one other, sorry, my 5 minutes left. Which brings me to another question, which is, we're obsessed thinking about when will those models do what we humans do? When will they rhyme? When will they reason? Maybe perhaps one day they will be conscious. As if consciousness or ability to reason were the ultimate achievements of neural networks in this universe. Just go and ask a chicken, you know, they don't have consciousness, right? So most likely. From their perspective, consciousness sounds like an amazing achievement. But it could be that there are properties of neural networks in this universe that neural networks could possess that we cannot even envision or begin to understand. So our obsession with thinking, when will those models be conscious, maybe just, hey, silly. Maybe they will have other properties as well. All right. But there's another interesting aspect for me as a psychologist, that all of this, of course, teaches us about potential spontaneous emergence and potential implications for how to build better models. And also there's a very interesting observation here for computer scientists who put a lot of effort trying to train the models to have theory of mind or trying to train the models to reason. And those attempts were very unsuccessful. And then they said, okay, forget about this. Let's just train the model to predict the next word in a sentence. And suddenly those models achieved uncanny ability to solve all of those other tasks that we tried very hard to train the model to do, and we failed. So that's an interesting lesson out there, right? Maybe we shouldn't be retraining the model, you know, to do what we want it to do. Just find another task, and this will emerge spontaneously. But it also could be a possible model that would, or a mirror that would help us to push our thinking about things like theory of mind or reasoning a bit further. Let me give you one example. I started by saying that we do not really know how system 1, system 2 in the human brain works. We have hypotheses, competing hypotheses, but we don't really know. And one of the hypotheses is that maybe system 2 thinking is just system 1 thinking, so intuitive generating of the next word, just going in cycles and using, you know, scratchpad of a short-term memory. Some people say, no, it cannot be, you know. Hey, it can be, because large language models can do exactly that. They can use their intuitive, like, next word generation to engage in chain of thought system 2 like reasoning. Not saying it means that it works like that in humans, but I'm just saying it's possible because this model does it. We know that it doesn't have all of those other magical processes that were ascribed to humans. It's a kind of yes, it's less magical and less magical thinking as a process. Another example is people that study theory of mind also have competing theories about how theory of mind works in humans. And one of the hypotheses there is maybe theory of mind is not a specialized part of our brain, some reasoning capacity of our brain. Maybe theory of mind is one of the parts of language capabilities. And why people would, and there's some evidence of this. For example, it turns out that children that were abused, like, kept in a basement until they were teenagers and didn't get language, they fail at theory of mind tasks, even the ones that do not really involve language. And then what happens is that as they learn language, suddenly the theory of mind, including nonverbal theory of mind, emerges. So people would say, hey, maybe there's a link there. And other people say, like, no, that's ridiculous. Why should it be related to language? It cannot be, or it cannot be. Now, hey, I'm again not making any claims about humans, but I'm just saying those models, they're just language models. There's nothing else there. And yet they can solve those tasks, showing that language ability seems to be sufficient to solve those tasks, supporting folks probably that argue the same for human brains. Yes, so that's what I just said. All right. And then there's yet another, how much time do I have? 1 minute. Okay, so I will just skip this last point and maybe move to, thank you very much. And let's move to the questions. Thank you. Sir.
Just a second. We do need.
Oh, I'm sorry. That's all right.
Raise your hand and I come.
Yeah. So the underlying theme behind large language models is two things: embedding and attention, as they call it. Are there any psychological counterparts to that which you see
In
theory of mind?
I do, but I think this would be, it would take us a bit more time. I actually think that we could probably learn how humans process language from looking how those models process language. Again, using it as a bit of a mirror, pushing us to think harder about human language. And I think attention actually is key there, but this I would need more time to explain it clearly.
All right, thank you.
It's too good of a question. I think we go from left to right.
One thing I'm curious about is it's hard to tell sometimes where something that a large language model can do, where it comes from, right? So GPT-4 versus GPT-3 have different training sets, but they also have different architectures, right? And if it's something that's produced by OpenAI, they're also tinkering with it, right, before they deploy it. So I'm curious if you have thoughts on where you think theory of mind is coming from, because cynically, right, OpenAI might try to make sure that it can do theory of mind tasks because that's cool, right? And so it's hard to say necessarily where this ability is coming from. Is it coming from like an improved training set that has more examples of theory of mind tasks? Is it something about the transformer architecture that's happening? Or is it something that like OpenAI has been fiddling with? Or is that kind of not something that you care about at this point?
This is it's a great question. And I think this is something we should be worried about. So we don't really know exactly how GPT-4 was trained. We actually have a very good idea. Hey, we have much better idea than our idea of how language center in a human brain works, okay? But we definitely do not know exactly. Now, luckily, we have tons of open source models, which maybe do not achieve, actually until today, do not achieve ChatGPT-4 performance, but are coming really close. And we see that similar ability to deal with those types of tasks emerges there as well, and we understand very well what the training process was like. Moreover, people make this following criticism. They say, hey, this model clearly has seen some theory of mind-like tasks or false belief situations in its training data. And I'm saying that's the core to my argument. Of course, it didn't learn how to rhyme while never seeing a rhyme. It learned how to rhyme because it needed it to be able to competently finish the sentences. And I would argue the same applies to humans. Humans learn how to rhyme or deal with theory of mind tasks because both in evolutionary past and in developmental past, they were exposed to those tasks. I'm not arguing that, like God, it emerged just out of nothingness just because. skills and abilities in humans and other animals and language models emerge because they're useful in survival and, you know, in their environment. And here the environment is the training data or us, you know, clicking thumbs up. So specifically, the theory of mind emerged because those models were exposed to them. Now, the explanation, there's another possibility, which is those models are much better than humans for sure at spotting delicate, subtle patterns in language. Like you put a comma somewhere in a paragraph, comma that changes the meaning of the paragraph. Many humans wouldn't notice because we're kind of sloppy readers. And those models, you know, they pay maximum attention at all times to everything that is happening there. So they're actually much more likely to notice that there's a comma, they're changing the meaning. So it could be that if I'm using false belief tasks that are different from the ones used in the past. So we wrote our own tasks. All of it was just made up for the purpose of this study. And next time we run this study, we'll have to make up a new set of tasks because maybe the model has seen, you know, or retained those already. So we try to create a diversity of tasks, but it's still possible that maybe model kind of extracted the essence from a training task and then applied it here. But as I showed you in this example of the Trojan horse code, and as you can experience yourself while chatting with those models, they seem to be having a theory of mind-like ability in, you know, all sorts of other, you know, less kind of standardized contexts. And folks, while theory of mind, you know, seems to be one of those things that is really controversial and people are just, you know, really easily saying, no, it cannot be because it's just what humans have. There are tons of those completely uncontroversial skills that emerge in those models, like rhyming, that people are like, yeah, of course it can rhyme. And oh, yeah, of course it can solve simple mathematical equations. And actually, you know, I'm a trained psychologist, so I'm also trained in this, you know, I'm trained to do a fair bit of magical thinking when it comes to human brains and seeing it as very special and much better than those other animals for sure, you know. But actually, the fact that now we see, hey, you have a bunch of equations that can do what you thought only human brain could do, and the brain is, you know, the size of a honeybee's brain, really makes me reevaluate a lot of my assumptions about human psychology. So I actually think that it will make us better social scientists to see that, you know, those models and us will make us ask harder questions by just seeing that now those models can do things that we believed before just humans could do. Madam.
Yeah.
But okay, yes, we'll make sure. Yes, go ahead.
I was wondering if on the emergent properties that you have seen or studied, if you have seen anything closer to abstract, symbolic, or logic reasoning, which arguably is been said that that's kind of what limits to get to AGI, right? So obviously theory of mind is one that you presented, but have you thought of addressing or looking into, again, this symbolic abstract thinking?
We did look into symbolic thinking, and the difficulty there is that with the newer models, they can solve tasks at the super Mihao level. So we increasingly have trouble designing tasks hard enough to just have those newer models fail on them. So for example, you can make a theory of mind-like task that instead of just having 2 characters, has 7 characters. And now they have beliefs about what other characters have beliefs of. And then you can, by the way, strip it off all of this story layer that for humans is just so helpful in anchoring our memory and so on, and just do it with like, imagine there's A and B and they know about C, but so you can really like boil it down to, you can make a story, but you can also boil it down to mathematical symbols. And then you can even replace those symbols with like some gibberish syllables to make it even more difficult, where humans would completely lose it because we're just not good at memorizing, you know, like things that don't make sense to us. And those models just ace it. And then scoring it is pain in the ass because I have to really slowly go with a piece of paper because the kind of out theory of mind's me in terms of its ability to solve those tasks. But there's another observation there, which is, and it's kind of not from my studies, that once you train the model to do one thing, it's easier for it to learn a new skill, which is not obvious, by the way, because it could be that knowing how to play chess interferes with its ability to learn how to play Go because maybe it's like biased towards chess. No, it turns out that if you pre-train the network to play chess, it's going to be faster at learning how to play Go. And it could go both ways, actually. But it seems essentially that, and then it's even easier to train it how to play Super Mario Brothers or whatever the next game you want to train it to do. So it seems actually that kind of like with human brains, there are some transferable skills, and it seems they're kind of benefiting from knowing how to do other things. So my intuition would be the future is few models doing all sorts of different things rather than specialized models doing each one their own thing.
Yeah. So I find it fascinating that your proposition is that emergent property comes from translation of languages. So we see that in the translation between mathematical language and logical language in the reasoning example. So I wonder whether you think about counterfactual reasoning. Could counterfactual reasoning also be an emergent property from translation of languages, right? So if we have a prompt, Gwen had a headache, Gwen took Advil, Gwen's headache is gone. Would the headache have gone had Gwen not taken the Advil?
Yes.
Would that be a prompt you can try?
Yes. And anybody can try it just in next.
How would I know this is because of this proposition? Emergent property.
How would you know in
comes from-
humans? Oh, well, you're putting me on a spot a little bit here. Let's think about this. But I would argue that you can test it in very similar ways to how you would test it in humans. So that's also, folks, this is a moment for social scientists, right? If I told you that at the town square here, a UFO has landed and from it emerged a bunch of non-human entities, and you can go and chat to them, and they chat in English, they respond in English. You can have them write your email to your mom or boyfriend or girlfriend, but also you can have them, like, you can just see who they are, ask how they feel, like test their cognitive properties. If you're a psychologist who says, I'm just going to go home and watch a TV show, I don't know, like, you're really interested in minds, okay? And yet, you are precise, that's precisely what happens. You know, OpenAI landed for you and other companies landed for you those alien thinking beings with their own brains and own ways around going about stuff. And many psychologists are like, oh, no, I'm going to study the same thing I was studied. I'm not even interested. Wow, I'm not going to pay $20 to talk to this alien. Guys, it's ridiculous. You are uniquely equipped as psychologists. You are trained to study black boxes. Now, computer scientists are designing those things, and they cannot predict. No one predicted that those models will be biased. They'll be able to translate between languages. No one predicted that they would be able to solve the theory of mind or reasoning tasks. People were surprised. Their engineers were surprised with what those things could do because the properties cannot be predicted from the properties of underlying neurons or neural networks. You folks, and I'm speaking to psychologists in this room, are uniquely equipped to help the world and yourself to understand how those things work. And maybe in the process, learn more about how human brains work.
We do one last question. I just wanted to actually get your own response to your very good questions, because I'm curious to hear if you want to, because to me, it sounds like counterfactual reasoning is a form of formal logic. And if you have a actually guess on that answer.
So I had not thought of it as an emergent property, which comes from the translation of languages, because I wouldn't know what the alternatives would be. But I have largely followed the causal AI lab from Columbia and UCLA. So I have a different way of thinking about counterfactual. But we can chat.
So is it possible that the ChatGPT, so you talked about theory of mind, right? So is it possible that the improvement of theory of mind in ChatGPT 4 is due to the data sets having additional tests that are designed to test the theory of mind that are also being used to train ChatGPT 4 as its data? So it's able to predict give better answers because it's already pre-trained with the tests that are already designed for testing theory of mind?
I think that's the entire idea, that those models learn how to do this because they had to deal with the task in the training data that required them to do this. Now, this would be problematic if they had exact the task I used in testing, or tasks that are very similar to the ones we used. But we tried to minimize this chance by designing our own tasks and then designing ways of messing up with them and doing controlled tasks as well. We just switch two words and so on, and then proving that those models still can now adjust the responses. So it doesn't seem like they just memorize the tasks or types of tasks. It seems like they have this generalizable ability to solve those sorts of problems.
Okay. Makes sense. Yeah.
Thank you, guys, and thank you for wonderful questions.